Let's now understand the relation between induced EMF and magnetic flux. By now we understand that induced EMF is of two types. First one is statically induced EMF. Second one is dynamically induced EMF or rotationally induced EMF. The expression for statically induced EMF is given by E is minus n d phi by dt according to Faraday's law of electromagnetic induction. And whereas the expression for dynamically induced EMF is given by E is dLV. In this video, we'll be finding out the relation between statically induced EMF specifically along with magnetic flux. Hence, we will consider our first equation, which is E is nothing but minus n d phi by dt. This negative sign in this right hand side of the equation is because of Lenz's law. Lenz's law states that the polarity of induced electromagnetic force will oppose the change in magnetic flux. Here n is nothing but number of turns and our magnetic flux is time variant. Let's assume the time variant magnetic flux is denoted something like this. Where phi m is my maximum magnetic flux value, and say my magnetic flux is varying sinusoidal in nature. Since phi m is constant, let's take it out. And if we differentiate sine omega t, it will be omega cos omega t. In order to compare two phasor values or time varying values, we have to make sure both equations are either represented as sine wave or cosine wave. So since this equation is in cosine wave and our flux equation is in sine wave, we will convert this induced EMF equation to sine wave. In order to convert sine wave to cosine wave or vice versa, it's easy to draw a phasor graph. So in the phasor graph, the positive x-axis will be sine and my positive axis will be cosine wave. If I wanted to convert my negative cosine wave to sine wave, I have to consider my sine wave and subtract an angle of 90 degree from my sine wave. Then my equivalent induced EMF equation will be something like this. Sine of omega t minus pi by 2. All right. And this will be my flux equation, which is now once we have represented both uh, waveforms in terms of sine, it'll be easy for us to compare. Let's say this being represented here. Since this is sine omega t, this will be in this x-axis, positive x-axis. This will be my flux. And as you can see here, our induced EMF is lagging by 90 degree, which is something like this. This will be our induced EMF. So from this phasor relation, it is easy to understand that whenever there is a maximum flux, our induced EMF's maximum value will be lagging by 90°. If you could plot the graph of magnetic flux and induced EMF along the time varying axis, it will look something like this. The blue color curve will be the magnetic flux, and our pink color line will be the induced EMF. As you can see from this graph, the induced EMF lags magnetic flux peak by 90°. This concept is important to understand the fundamentals of electrical machines for further simulation analysis. Let's consider an inductor wherein the magnetic flux is phi and it has its corresponding current I flowing through it. The final phasor relation between induced EMF I and flux will look something like this.